The world before the experiment. In the late 19th century, the world of science felt like a place of certainty. Physicists believed they understood the universe with absolute confidence. Light, they thought, traveled through a mysterious, invisible substance called the luminiferous ether. Just as sound requires air to travel, and waves require water, light supposedly needed this invisible medium. The ether was everywhere. It filled space, permeated the earth, and carried the sun's rays across the cosmos. No one had ever seen it, yet it was considered undeniably real. At the time, the laws of physics seemed solid and unchanging. Space and time were absolute. Motion was measured against a fixed backdrop of the universe, and light was assumed to behave predictably. The universe was orderly, logical, and entirely comprehensible, or so it seemed. The certainty was almost comforting. Scientists could build machines, calculate planetary motion, and predict natural events with confidence. It was a universe governed by reason, where the invisible threads of the ether kept light and matter on predictable paths. Into this world of apparent certainty stepped Albert Michelson, a meticulous American physicist, and his collaborator Edward Morley. Their mission was modest but precise, to detect the motion of the Earth through the ether. They wanted to measure what they called the ether wind, the subtle change in the speed of light caused by the Earth moving through this invisible medium. The question seemed simple. If light needed a medium, then moving through that medium should change the time it takes to travel in different directions. To achieve this, Michelson and Morley devised an experiment that was elegant in its simplicity and brilliant in its design. They built an interferometer, a device capable of splitting a beam of light into two paths, sending the beams along perpendicular routes, reflecting them back with mirrors, and then recombining them. If the Earth moved through the ether, the two beams would meet out of sync, producing shifts in an interference pattern that could be measured. In other words, they would see the wind of the ether through the way light interfered with itself. The world watched this small experiment with quiet interest. For most scientists, it was expected to confirm what everyone already knew. The ether was real, light traveled through it, the experiment would prove it, and the laws of physics would remain intact. Confidence was high, not just in the experiment but in the very foundation of science itself. It seemed impossible for reality to contradict centuries of observation. Yet, even in this confident age, subtle whispers of doubt lingered. Previous experiments had failed to detect the ether consistently. Tiny anomalies in measurements, strange inconsistencies in light's behavior, and the repeated absence of detectable ether hinted that something might be off. These anomalies were usually dismissed as errors, imperfections in equipment, or limitations of the methods available. Few dared to imagine that the universe itself might be playing a trick. Michelson and Morley were careful, patient, and methodical. They mounted the interferometer on a massive stone slab to minimize vibrations, controlled temperature variations, and performed hundreds of measurements with painstaking precision. They were not trying to overthrow physics, they were attempting verification, the bread and butter of scientific inquiry. And yet, their experiment would soon do something none of them, or anyone else, could have predicted. The stage was set. The world believed in absolute truths. The ether was real. Light's behavior was predictable. Space and time were constants. Science, as humans understood it, was unshakable. And then, in a quiet laboratory, with light bouncing across mirrors and beams split into invisible paths, the universe prepared to reveal a secret. A secret that would quietly shatter centuries of certainty, a discovery that would force humanity to rethink the very nature of reality itself. In that era, no one realized that the world before the experiment and the world after it would never be the same. Michelson and Morley were about to perform a small experiment on a stone slab in Ohio, but what it revealed would echo across physics, philosophy, and the way humans perceive the universe. It was the calm before a storm that would change science forever. The experiment that should have failed. The year was 1887, and the scientific world was confident. The ether existed, light traveled through it, and the rules of the universe were steady, unchanging, and predictable. Into this world, Albert Michelson and Edward Morley brought their quiet determination, armed with a machine designed to confirm what everyone already believed. Yet the universe had other plans. Their tool, the interferometer, was a marvel of precision. It was deceptively simple, a beam of light split into two, sent along perpendicular paths, bounced back by mirrors, and then recombined. If the Earth was moving through the ether, One beam should travel slightly faster or slower than the other. This tiny difference would create a measurable shift in the interference pattern, a ripple visible to the careful eyes of the scientists. Michelson and Morley conducted the experiment on a massive stone slab, isolated from vibrations, perfectly leveled, and shielded from heat fluctuations. Every variable was accounted for. Their measurements were meticulous. They rotated the interferometer slowly, observing the interference fringes shift as the Earth moved, expecting the results to confirm the ether's presence. And then, nothing happened. No matter how they adjusted the instrument, no matter the angle or time of day, the expected shift in light never appeared. The interference pattern stayed exactly the same. The ether, the supposed medium of all light, had left no trace. It was as if the Earth moved through empty space, undisturbed. The result was subtle yet profound. Their experiment, designed to verify a certainty, had produced a complete contradiction. At first, Michelson doubted himself. Could the instruments be flawed? Could temperature variations, vibrations, or even human error have masked the effect? Morley checked and rechecked every calculation, every alignment, every mirror. They repeated the experiment in every conceivable way, running test after test with relentless precision. Each time, the result was the same, zero difference. The null result was impossible. The scientific consensus was that ether must exist. To claim otherwise was heretical. Yet the data could not be ignored. Nature, it seemed, refused to obey expectation. Every assumption about the ether, absolute space, and the behavior of light was suddenly in question. Some contemporaries suggested explanations. Perhaps the ether was dragged along by the Earth, or maybe it interacted with matter in ways not yet understood. Others dismissed the experiment entirely, thinking some subtle flaw had caused the unexpected outcome. But Michelson and Morley's work was rigorous. The result persisted. It could not be explained away. What made this moment extraordinary was not the experiment itself, but the implications of its failure. The ether, the foundation of physics for decades, was nowhere to be found. Scientists had built entire theories on the assumption of its existence, and now the very ground beneath those theories seemed to vanish. The world of absolute space and absolute motion, long taken for granted, was being questioned by a quiet stone slab in a laboratory. The null result became a turning point. For years, it was an anomaly, a puzzle that refused to fit into existing models. Yet anomalies in science often herald revolutions. Michelson and Morley could not have known the full impact of their findings at the time. They were meticulous, careful, and humble. They did not claim to have overturned the laws of physics. They simply reported what they had observed, a universe that did not behave as predicted. This experiment, small and unassuming, planted the seeds of a profound transformation. It forced physicists to confront a terrifying possibility: the universe might not be as predictable or intuitive as previously believed. The Earth did not move through an invisible ether. Light did not require a medium. Space and time were no longer absolute. Reality, in its most fundamental form, was more flexible and strange than anyone had dared to imagine. Michelson and Morley had performed what was intended as a routine verification, yet the result was nothing short of revolutionary. The calm, methodical experiment had cracked open the door to a new understanding of the cosmos. Science, for the first time in centuries, was forced to question its own foundations. This moment, quiet, precise, and almost invisible, would echo across physics and philosophy for decades. It would inspire the work of Albert Einstein and the birth of relativity, reshaping our understanding of space, time, and reality itself. The experiment that should have succeeded instead failed in the most meaningful way, and in that failure, the universe revealed its deeper, stranger truths. Reality breaks. The year is 1887. Michelson and Morley's experiment has been completed. Their interferometer, meticulously aligned, has delivered its impossible verdict: no ether, no detectable ether wind, no confirmation of centuries of scientific assumptions. On a quiet stone slab in Ohio, the universe had defied expectation. But what did this mean? At first, the null result was treated with caution. Scientists were reluctant to discard ideas that had dominated physics for decades. The ether had been a cornerstone of understanding. Light needed a medium, space was absolute, and time marched uniformly forward. To suggest otherwise felt almost heretical. And yet, the evidence was clear. The ether did not exist. Reality was not obliged to behave according to human intuition or centuries of theory. This realization sent ripples through the scientific world. If light could travel at a constant speed, regardless of the Earth's motion, then the old concepts of space and time were incomplete. The framework of Newtonian physics, long considered infallible, suddenly appeared provisional. The rules that governed reality were no longer fixed. Space and time, once absolute, now seemed intertwined, flexible, and relative, a revelation so profound that it would take decades for the full implications to be appreciated. It was a small experiment, a tabletop device, but its consequences were immense. The universe was now understood to be stranger than anyone had imagined. The fundamental laws of physics, so precise, so dependable, were revealed to be approximations rather than ultimate truths. Scientists realized that they had been measuring the universe from within a framework that was incomplete, and that true understanding required rethinking the very nature of existence itself. Over the next 2 decades, this insight would inspire a revolution in thought. In 1905, Albert Einstein, building on the impossibility demonstrated by Michelson and Morley, proposed the special theory of relativity. He suggested that the speed of light is constant for all observers, no matter their motion, and that space and time are not separate entities but part of a unified fabric, space-time. Time could stretch, lengths could contract, and simultaneity was no longer universal. The universe had revealed its elasticity, its hidden rules that contradicted everyday intuition. The philosophical impact was equally profound. If something as fundamental as space and time could behave counterintuitively, what else might be misunderstood? Reality was no longer a fixed stage on which events unfolded predictably. Observation, measurement, and understanding became questions of perspective, context, and limits. The universe could surprise, confuse, and confound. Human knowledge, once thought to be climbing steadily toward certainty, was reminded of its fragility. The Michelson-Morley experiment became a symbol of science's courage. It was a testament to the idea that reality does not bow to expectation. Experiments, not intuition, define truth. And yet, the truth revealed by this experiment was strange, unsettling, and beautiful. It showed that nature can defy human logic, that the cosmos operates on principles far more subtle and intricate than our senses can detect. Technological and scientific breakthroughs of the 20th and 21st centuries owe their existence to this realization. GPS satellites, particle accelerators, nuclear physics, and space exploration all rely on concepts that were unimaginable before Michelson and Morley. The null result of a small, seemingly routine experiment paved the way for humanity to understand black holes, time dilation, and the vast, elastic fabric of space-time. But perhaps the most enduring lesson is philosophical. Reality, as we perceive it, is only a shadow of the deeper truths that govern the universe. The experiment teaches humility. The cosmos is not obliged to conform to human logic, and certainty is always provisional. To explore, to question, and to test, that is the essence of scientific inquiry. In the quiet of their laboratory, Michelson and Morley had done more than measure light. They had broken the comfortable illusions of reality, revealing a universe that was stranger, more flexible, and more astonishing than anyone had dared imagine. Their experiment was small in scale but colossal in consequence. It reminded humanity that science is not just a collection of facts, it is a process, a dialogue with nature, and sometimes, a confrontation with its most unsettling truths. The universe, it turns out, is less predictable, more mysterious, and infinitely more wondrous than it ever seemed. And the journey of understanding, sparked by a single, unassuming experiment, was only beginning. The world after. The quiet laboratory in Ohio, where Michelson and Morley had conducted their small, unassuming experiment, had set off a chain reaction that would forever change humanity's understanding of the universe. The null result, an absence of the predicted ether wind, was not just a scientific anomaly, it was the beginning of a revolution. It demonstrated that the universe does not bend to human expectation, that reality is stranger and more flexible than intuition allows. By the early 20th century, the implications of their work became impossible to ignore. Albert Einstein's special theory of relativity, inspired in part by the Michelson-Morley experiment, formalized what had seemed absurd just decades earlier. The speed of light is constant, and space and time are not absolute. Instead, they are intertwined in a fabric called space-time, stretching and contracting depending on motion. What had once seemed immutable, time ticking evenly, distances fixed, simultaneity universal, was now understood as relative. This conceptual leap transformed not just physics, but how humans perceive their place in the universe. Space was no longer a passive stage. Time was not a fixed ruler. Observation itself became an active part of reality, a principle that would later echo in quantum mechanics and the exploration of the subatomic world. Humanity had been forced to accept that reality is not always intuitive, and that curiosity, rigor, and experimentation are the only reliable guides to truth. The ripple effects of this revelation are felt even today. Modern technologies, from GPS satellites to particle accelerators, from nuclear reactors to space telescopes, rely on the principles that emerged from understanding the limitations of classical physics. GPS, for instance, accounts for the relativistic effects of both Earth's gravity and satellite motion. Without this adjustment, navigation systems would accumulate errors of kilometers every day. All of this traces directly back to the quiet measurements on that stone slab over a century ago. Beyond practical applications, the Michelson-Morley experiment left a philosophical mark. It reminded scientists, thinkers, and the public alike that certainty is provisional. What we see, measure, and experience is only a part of a far larger and more complex reality. The universe does not conform to human expectations, and progress comes not from dogma but from questioning, testing, and sometimes failing. In science, failure is not the opposite of success, it is a path to deeper understanding. The experiment also reshaped the culture of science itself. Scientists learned to embrace uncertainty, to seek anomalies, and to pay attention to results that challenge assumptions. The notion that reality can surprise us became a guiding principle. It was a lesson in humility. Human knowledge is powerful, but always incomplete. And yet, within this incompleteness lies the thrill of discovery, the excitement of exploring a cosmos that is both knowable and endlessly mysterious. Even in popular culture and thought, the impact is evident. The idea that the universe is stranger than it seems inspires curiosity, creativity, and imagination. Science fiction, futuristic technology, and even philosophical inquiry carry echoes of the lessons learned from this single, precise experiment. Humanity's perception of the universe, its vastness, complexity, and unpredictability, was permanently expanded. Perhaps the most remarkable aspect is how a single, seemingly minor experiment reshaped everything. Michelson and Morley were not seeking fame or revolution. They were pursuing precision, curiosity, and truth. And yet, in doing so, they revealed the fragility of human certainty and the resilience of curiosity. A tabletop interferometer, mirrors, and beams of light had rewritten our understanding of reality itself. Today, as satellites orbit the Earth, as scientists probe the cosmos, and as engineers build technologies unimaginable in 1887, the legacy of that experiment endures. It is a testament to the idea that science advances not when it confirms what we already believe, but when it confronts what we think is impossible. It teaches that progress is driven by questioning, by observation, and by the courage to follow evidence wherever it leads. The day science changed forever was not marked by fanfare or headlines. It was a quiet morning in a laboratory, a stone slab, and two scientists watching light bounce between mirrors. Yet, in that quiet moment, humanity glimpsed a universe far stranger, far more beautiful, and far more profound than anyone had imagined. The world after the Michelson-Morley experiment is not the same as the world before, and every modern breakthrough, every journey of discovery, is built upon the courage to confront the unexpected and embrace the unknown. Science, it turns out, is not a catalogue of facts. It is a journey, a conversation with reality itself. And that conversation, sparked by a single, simple experiment, continues to this day, reminding us that curiosity, rigor, and wonder are the forces that drive humanity forward.